let's finish. In fact, we're going to very quickly summarize on routing. We've covered enough. We know what is routing. We know that we can have different metrics to measure least cost. With fixed and adaptive routing, we use routing tables and we calculate the least cost paths and store that information in a routing table. An alternative strategy we saw was flooding, just send to everyone, and of course eventually a packet will get to the destination, but very inefficient. So there are different strategies. There are different metrics that can be used for routing. We need some way to distribute information. In that question we just said that we can either get information from our neighbours or maybe we can ask our neighbours' neighbours for information. So we need routing protocols to distribute that information, and there are different routing protocols. And we use routing algorithms to calculate least cost paths, like Dijkstra algorithm can calculate the shortest path from a source to multiple destinations. We're not going to go through the details of all those different options, we're just mentioning them. So we're going to skip over these slides. This gives an example of how we could distribute information between nodes. That is, we're going to skip the details of this example. You can read through it in your own time. So we're going to summarize and move on. And this is really a summary of both routing and switch networks, the previous topic. Very basic. We can form communication networks by connecting multiple devices across multiple links. And we deliver data from a source to destination via intermediate devices using the concept of switching, where we send to an intermediate device and the device sends it out onto one of the many possible output links. It's a switch. It either goes this direction, or this direction. We can use either circuit or packet switching. We've gone through the details of those techniques. So that's about getting the data from source to destination. Routing is about determining the best path from source to destination. So we usually treat them separately, although they're both needed to achieve our end goal. And as we just said, there are different types of metrics, different strategies, different algorithms, different protocols available for use. And normally it's up to the organisation that runs the network to choose what they want. One company, one internet service provider may use the metric of delay. Another company may build their network and use a different metric. It's up to their business goals, their policies to choose what are the best metrics, what are the best protocols to use in their case. In practice, circuit switching developed for telephone networks and it was therefore designed for carrying a constant amount of traffic. In a telephone call, you're sending the same amount of data during that call, or it's reasonably constant. It doesn't change much. Still in use today, telephone networks and the infrastructure still in use. Packet switching developed where we break the data into smaller chunks, into packets, and turns out that it's much better, much more efficient when we have a varying amount of data to send. Because I can send a burst of packets, they may be queued up at a packet switch, and then eventually they'll be sent. And then I may send no packets. So this varying sending rate is well suited for packet switching. Or packet switching is well suited for this varying sending rate. Packet switching is the concept used in the internet today and most new wide area networks. And in fact, it's not so simple that you use just one or another. The telephone network uses circuit switching, but internet access in some parts operates over the top of the telephone network. So in fact, we're using packet switching and circuit switching at the same time. The best example, when you use dial-up internet, what you would do is you'd make a connection from your home modem to some internet service provider. That was using circuit switching. But then for delivering your data across the internet was using packet switching. So in fact, they're both in use. There are different algorithms for calculating the shortest path. We haven't touched upon how they work. You may have seen them in other courses. We're not going to go into details. Dijkstra, Bellman Ford, and others. And there are trade-offs between different routing protocols and the algorithms. And the best one depends on the design of the network, how big it is, how many nodes, how many links, how much data does it carry, the amount of traffic in the network, and the rate at which it changes. That is, are new nodes being deployed in the network every day, or does it stay the same for an entire year? So those factors impact upon what's the best approach for routing. And that finishes this topic on routing. We're going to move on to the next topic. These concepts are mainly applicable for wide area networks. Also, some are used in local area networks, our next topic, but mainly switching and even routing, especially adaptive routing, is applicable for wide area networks, when we want to have a large network covering a city, a country across the globe. Let's look at local area networks. And let's today try and look at how the basic approaches for designing a local area network. First, what is a LAN? How to design a local area network, and then maybe tomorrow we'll get into the details of how some technologies work. So wide area networks, we know, cover a large geographical area, like a city, between cities and so on. Local area networks, we're talking about within a campus, a university campus, a company campus, within buildings, within homes. Local area networks connect the end user devices over a small geographical area. Wide area networks don't necessarily connect end user devices. That is, my PC may not directly connect to a wide area network. My PC may connect to a local area network, and then a packet switch in my local area network may then connect onto the wide area network. So sometimes the end users don't directly connect to wide area networks. A local area network is normally owned and operated by the organisation that is using the network. That is, the cables of the network devices are owned and operated by SIT in our local area network. That is, connecting all of our lecture PCs, all of our office PCs together into a local area network. All the cables, all the infrastructure is owned and operated by SIT. The network is designed by the computer centre at SIT. And the end user devices are owned and operated by SIT. Whereas in a wide area network, normally the case is that the network infrastructure is owned and operated by an independent company that is not, or that the users are not part of. That is a telecommunications provider, an internet service provider. So the connection between this campus and our other campus, the wide area network connection, we pay another company to provide the network infrastructure, to provide the cables, to provide the switches and the different devices. That means we normally have more control over the design and the building of the network in a LAN than in a wide area network. And there are often many more design choices to make and different technologies to choose from, or different approaches. Whereas a wide area network, the network itself is leased to the end users. So the end users pay another company to use their network. Local area networks typically, not always, but in most cases have higher data rates or support higher data rates than wide area networks. One reason is that a local area network needs to support communications from the internal computers to computers on the internet, external. Therefore, the network needs to support that amount of data, as does the wide area network connection. But a local area network also needs to support communications between users inside the network, from my computer to a computer in an office. That data traffic doesn't go out onto the wide area network. So normally we need our capacity in our LAN to support both internal and external communications. Also, because of multiplexing and also because of the cost of technologies, then you'll find that there are typically higher data rates in LANs than in wide area networks for the same cost. Not the best example, but I think one that you can relate to is your local area network in your home or in your office may support 100 megabits per second or even 1 gigabit per second, but your connection from your home out onto the internet is only measured in megabits per second, 1, 6, maybe 10 megabits per second. Let's look at 3 key decisions when designing a local area network. How do we connect to computers across SIT so that they can all communicate with each other? We need to consider the topology of those computers and the links between those computers. How do we arrange the nodes so that they connect with each other? What transmission medium should we use? Optical fibre, coaxial cable, wireless, twisted pair, which one's best for LANs? And finally, we'll get on to how do we control who can communicate at what point in time. So we'll explain what is medium access control. Let's go through the first one. Our goal, if we have multiple computers in our campus or in our building, we'd like to be able to connect them all together. And that will form our local area network. And allow any user to communicate with any other user. That is, any end user device, a PC, a laptop, to communicate with any other. Just internal to the building or the campus. So how do we arrange the end user devices, the stations, such that we can achieve this? There are different topologies that we can use. Let's go through them. The first topology we'll look at, which is not commonly used, is a mesh topology. A mesh topology, if we have 4 computers, to keep our LAN simple for an example, these are our end user devices, our stations, say 4 PCs, and we want to connect them all together. A mesh topology, when we say mesh, we mean a full mesh here. We connect every computer to every other computer via a point-to-point link. That is, for computer A to communicate with computer B, connect them via a cable, via a link. So if A wants to send data to B, they simply send their data across this link. And it will reach B because it's a point-to-point link. And we know a point-to-point link, we just have 2 devices attached. One device sends, the other one's going to receive. And of course, A wants to be able to potentially communicate with the other stations. So A would need point-to-point links to the other 2 stations as well. And similar for the other stations. We'd need 6 links if we wanted to have a full mesh topology using point-to-point links with just our 4 stations in the network. So very simple. A node, depending on the destinations, simply chooses the appropriate link if they want to send data to that destination. If A wants to send data to C, send your data on this link. If you want to send to D, send on this link, and so on. So that's a full mesh. Note, so with our simple example with 4 stations, we need 6 links to allow any pair to communicate, assuming they are full duplex links, bidirectional. If A can send to C on this link, we assume C can send to A on the same link. And each station needs 3 links, or is attached to 3 links. In other words, each station needs 3 network interface cards. NIC is short for Network Interface Card, a device which interfaces us to the network. This is a LAN card or a network interface card. So we plug our cable into the socket, and that provides, when we transmit onto this link. In this case, we need 3 of these per computer because we have 3 separate links attached to that computer. That's a problem. Here's a simple LAN. Now in SIT we have 100 stations. How many links? How many links do we need? Not quite. That's too many.
No, 99 factorial.
It turns out it's 100 times 99 divided by 2. If you look, you need to count the number of pairs.
Oh, okay.
Here.
That is the full duplex.
Which is approximately what? Almost 5,000 links. Less than 5,000, 4,900 and something. So if we have just 100 computers in SIT, which is about reasonable, and we want to connect them in a full mesh topology, we want to do this, we need almost 5,000 different cables going across the campus. That's a lot of links. How many network interface cards per station do we need? How many network cards? How many? 99. We want to connect to 99 other stations. I don't need to connect a link to myself. We use these, we have a link going to every other computer. If there are 100 computers in total, my computer needs to connect to 99 other computers.
And why not my computer have no NIC?
My computer has 99 NICs. So this computer has 3. So if this is your PC, you have 3 of these cards in the back of it. And you have 3 cables plugged in, 1 into each of the socket, into each of the network interface cards. These are different links. How many PCs can handle 99 network interface cards in them? Not many. You physically cannot put them that many in. So a mesh topology is not appropriate for most local area networks. In theory possible, but only really useful for very small configurations where we have a few nodes, or if we need high redundancy. We'll see some advantages of it shortly, but not really applicable for most LANs because too many links, too many network interface cards needed per node. So let's look at some other topologies. A bus topology. We have a single link and all our stations connect to that single link. And when they transmit, their transmission propagates through the entire link, across the entire link. So in this case, we have our 4 stations. Think of this as the single link, the solid line at the top. Each of the stations attach to that link. There's some terminology, they use a tap to attach to that. But you can think of, again, each station has a special network interface card, and there's a cable going past and it just connects into here. That is the bus, the card attaches to that bus. It's slightly different than this. And this is a multi-point link. When one station transmits, the signal can go to multiple destinations. So if this station transmits, you can think the signal propagates across the entire bus. Anyone attached to that bus can receive that signal. So that's different from here. These were point-to-point links. Now we have a point-to-multi-point link, or generally a multi-point link. Here, just 2 devices attached to each link. We just have multiple links. Now we have one link and have many devices attached to that. What we do, we transmit onto the bus. The signal propagates across the entire bus. When we transmit our data, we transmit it as frames, where a frame contains some data plus a header. And we need now in the header at least a destination address. If we say this is A, B, C and D, if A wants to transmit data to C, it transmits a frame onto the bus, the signal propagates across. This station B, you can think, sees that signal, recognises that it's destined to C, it's not destined to B, ignores that frame. And when C sees the frame, it sees it is the destination and takes a copy. And when D sees the frame, it ignores that frame. So we transmit our frame and everyone potentially receives that frame. Therefore, to make sure that the right station receives the data, we need addresses in those frames. We did not need addresses for our mesh topology. If A wants to send a frame of data to B, it simply transmits across this link. There's only one other station attached to this link, and it's B. Therefore, it's guaranteed that B is going to receive it, no one else. So we don't necessarily need addresses in this topology. We do need them in a multi-point link. We'll come back to the pros and cons. An example of the transmission. Here, C wants to transmit to A. C transmits a frame onto the bus. It has the destination address A in that frame, in the frame header. It is transmitted across the entire bus. B, the frame is not addressed to B. B ignores that frame. B sees it, effectively receives it, but does not take the data from the frame. It ignores it. A sees a copy of the frame, recognises it's the destination, takes a copy of that frame. The frame keeps going. If our bus is longer, then it keeps going. And in fact, we have special terminators at the endpoints of that bus so the signal doesn't propagate back.
When the packet collect at the three-way, it's duplicate to be
you think you take a copy. So the signal is propagating along here. This takes a copy.
And it's not belong to that one. This copy.
Yes. So in effect, everyone receives a copy of the frame. So this computer has that frame in memory, but when it detects the destination is not itself, it simply deletes it from memory. It discards that frame.
So we can possibly access the information from C.
For sure, B can see the data that C sent to A. And
so everyone can get the information.
Everyone can see the data. So and this approach was used in past local area networks. So if we use this in SIT, when I transmitted to my computer in my office, if we used a bus topology, then every computer on that bus could see the data that I sent. So that was a security problem. But normally in a LAN, you trust the people who are in that same LAN. So if I connect a LAN between SIT office computers, then we trust who's in that, attached to that network. So security is a potential problem, but in practice it's not a big issue internal to companies. The advantages of this, especially compared to our mesh, how many links do we need? How many links do we need in our bus topology? In fact, we think we just have one. We have one cable that passes by every computer in the network. So think of one long cable that just goes past every computer, and it just has a special attachment to the network interface card. So we think we just have a single link that passes by every computer. Each computer attaches to that one link. Much simpler than having 5,000 links in SIT. We just have one cable that passes by 100 computers.
The branching not count the link.
Yeah, it's direct. You don't need a separate cable, in fact. And also, we just need one network interface card per station. If I have 100 computers in SIT, each computer has a network interface card that attaches to the bus. So much simpler from the network installation point of view. One cable and one network interface card. Although sometimes if we have a lot of computers and we want to cover a large distance, having a single cable that goes past all computers is not very convenient. We need to lay it through all the walls and pass every possible computer with the one cable. That's not possible in some cases. And in fact, because of the distance at which your signal propagates, there are usually limits on the number of stations that can attach to a single bus. You cannot attach 1,000 stations to a bus. There are limits. Because we have a shared medium, in that we have a point to multi-point link, we need some way to control who transmits, who can access that medium. Here's our network. Our bus. If A wants to send data to C, A transmits a signal onto the bus. And it goes all the way along the bus. It's going to be received by everyone. C is going to take a copy. The others will ignore it. If at the same time D wants to send data to B, they transmit a signal on the bus. The two signals interfere with each other. That is, when both people are sending signals on the same medium at the same time, from the receiver's perspective, they cannot understand what was transmitted. So if two people transmit at the same time, the receivers will not understand or will not be able to receive the frames which were transmitted. They would see it as noise or as random variations of the signal, because those two signals combine together and they do not follow the expected pattern of what the receiver expects to receive. The receiver cannot decode it into zeros and ones. So we have a problem. If we have a shared medium where if one transmits, everyone receives, that's a shared medium, then we need to somehow control such that we do not have such interference. So we need special protocols to share the medium amongst those nodes. We'll cover those special protocols or describe them shortly. But it adds complexity to the protocol, the design of the network. In our mesh network, what happens if I cut this link? It fails. It's okay for most people. D and C cannot communicate, of course. If we cut this link, they do not have a link between them. So that's a problem. But everyone else can communicate. D can communicate to B and A, C to A and B, A to B and D, and also C. So if we cut one link, we have a fault in one link, still most others can communicate in a mesh network, or a mesh topology. In a bus, if we cut this, we have a problem. In fact, usually Yeah, these pairs cannot communicate with each other. In practice, normally the design of a bus is that if you have a failure, normally, or in many cases, the entire network may fail, because often a network needs other protocols to communicate with everyone. So a failure in a bus topology can lead to the failure of the network, or significant failure in terms of communications. That's a problem with a bus topology. Bus networks were used in early LANs, company and home LANs, Ethernet networks, but have been mainly replaced by star networks. Ring topology. Connect the stations together using point-to-point links in a circular manner, where those point-to-point links attach to some special repeater device. So here's our 4 stations. We have 4 point-to-point links. And these black boxes, they could be built into the network interface card, in fact. So what we'd have is a special network interface card where we have 2 cables plugged into it for each station. For this station, we have 1 cable coming from this node and 1 going to that node. So we have 2 cables coming into each station. So the signal comes in and it is repeated and sent out on the other link. And what we do is we have unidirectional point-to-point links. We transmit our signal in one direction around the ring. And normally the signal goes all the way around the ring, independent of who is the destination. Let's go through our example and then come back to the comparison. So here we have a ring of 3 stations. C wants to send data to A. It's again a shared medium. We have the issue if 2 people transmit, we'll have interference. In this example, the ring goes in one direction, in the direction counterclockwise here. C transmits a frame, destination A. The frame contains the header, including the destination address of station A. It's transmitted across the first point-to-point link, received by B. B is going to transmit it across the second point-to-point link, repeat that signal. But also B notices that it is not the destination, so it does not take a copy. So all B does, receives and transmits across the next segment, across the next point-to-point link. As does every other node, just transmit across the next segment. If you're the destination, take a copy as well. So A is the destination, A transmits across the next link, N takes a copy of that frame, because the data is destined to A. When it comes back to the original source, C does not transmit across the next link. That is, it only goes around the ring once. Why did A send it on when A was the destination? What's an advantage of that? Normally in a ring network we transmit our frame all the way around the ring, even if it gets to the destination before it reaches the original source again. So in this case, A received a copy and also transmitted it back to C. That's very useful if you want to do something like transmit a frame to multiple destinations. Let's say we have another network going in this direction. A has a frame to send with some data, and it wants to get to destination the same data to both D and E. That is the destination, in this case, there are 2 destinations. So what we do, using our ring network, transmit to B, B transmits to C, C transmits to D, D takes a copy because D is one of the destinations, D transmits to E, E takes a copy, because E is also a destination. E transmits to A.
A is sender and E is the destination.
A is transmitting and both D and E are destinations.
On D and E.
Two destinations.
Two destinations.
Sometimes we'd like to send data to multiple stations. So that's very easy in a ring network. Because the frame passes all the way around the ring, simply include the header, the destinations, or some identifier of the multiple destinations. Whoever's in that set of destinations takes a copy. How many links do we need in our ring network of 100 stations?
1 link.
How many links in our ring network?
Ring.
Links. How many cables?
Oh, okay. 1 cable บวกกับ101.
100.
Oh, 100.
Here we need three stations. 1, 2, 3. So one point-to-point link per station. 100 stations, 100 links.
100 station, 100 link.
And we can think of 2 network interface cards per station, or 1 special interface card.
How you count?
Think of every station has 2 cables coming into it, so we need 2 sockets per station.
100 station.
So not much different from a bus topology. We could say that there are 2 network interface cards per station because we have 2 cables coming into each station. In practice, it would be implemented as 1 card, but as a special card with 2 sockets. Think of this station has 1 link coming into it and another link. It needs 2 sockets to plug those cables in. 2 network interface cards per station, 1 link per station in the network.
Okay. You will not
Yeah.
count the branch also.
They both go in.
Only 1 and 1. These 2 links come to 1 together.
Yes.
One computer and 2 in
Yes.
coming link.
Yeah. So similar in terms of complexity to a bus topology. Much better than a mesh topology
Much better.
in terms of the number of links and network interface cards that we need. Still a problem, if I cut this, the network fails. Because most ring networks rely on sending all the way around. So if I cut 1 link, the network fails. So that's a disadvantage. But in fact, it's an advantage in some scenarios. Not so much in LANs, but in citywide networks, where we have networks, or even between cities, ring networks are often used, not because of this, that if we cut it, it fails, but if we cut or this link fails, we can quickly identify where the failure is in the network. If this link fails, by sending a packet around, we will quickly know that this is the link that failed. If we have a network across Bangkok and we're providing connectivity to many customers across that wide area network, not a LAN, and we use a ring topology, if someone is digging a hole and cuts a link, physically breaks that link, we can quickly detect where that failure is. And in fact, detection of failures within a matter of milliseconds is very important when we've got internet service providers providing networks. Send a signal around and detect who receives the signal.
Oh, okay.
And you'll quickly find which one doesn't receive it.
The one who receives the signal will acknowledge that he
Yeah,
received it.
yeah.
And we see then which one is missing from.
Yes, so we can see which segment is missing to find that. That's not so much relevant for the local area networks, though. So ring networks, similar to bus networks, we need to share the medium. If 2 people transmit, they'll interfere with each other. Sometimes there's a performance problem of traffic just goes in one direction. That is, it can incur a large delay to get back to the original, or to get to the destination. Generally easy to install and reconfigure, easy to identify faults. Used in old local area networks, IBM had a token ring style LAN. Not so much now. the concepts are used in metropolitan area networks, city area networks, and some wide area networks. That's sort of off topic because we're focusing on LANs. Last topology, a star topology, have some central device, attach all your stations to that central device via point-to-point links. All the data goes from a station to the central station, and that central station then sends it to the destination. Usually there's either 2 point-to-point links or full duplex links, so we can send to the station and receive from the station. How many links do we need? 100 nodes in SIT, how many links? 100. One computer, how many links from, in a star topology, every station has a link to a central node. So 100 links if we have 100 stations. How many network interface cards per station? 1. So very simple for a station. We just have one network interface card, one cable going into it, and that cable going to a central device. The problem is that we rely on this central device. If this central device fails, the entire network fails, because everyone sends via that. If this node fails, or if this link fails, of course this node cannot communicate, but the others can still communicate with each other. Similar in terms of link failure. Similar in terms of link failure, yes, but if the central device fails, much worse than the others because the entire network fails. We're highly dependent on this.
If you want to destroy, you destroy switch.
Yes. Easy to install. We just need one link from every computer into this central device. And it's what's used in most LANs today. Our SIT network, every computer, we see we have a cable, one network interface card. This cable actually plugs into a socket, goes up and goes through the ceiling cavities and down to the 3rd floor. And in the office on the 3rd floor, there is some switches, and they all have cables plugging into them from each of the computers in SIT. There's a room on the 3rd floor with the switches. Here's a switch. Very exciting to look at. You can see it has 8 ports, allowing 8 stations to connect to this switch and communicate in a small LAN. And you have switches. Your home ADSL modem or your wireless access point normally also acts as a switch. This one has, of course, it's for wireless communications, but in addition to that, it has 4 ports, which is simply a switch. So that is a switch as well, in that 4 computers can connect and they can all communicate in this star topology. How many links for star topology? How many links for 100 stations? Star topology? 100. Now we need to, do we call this 1 or 2? In fact, nowadays most links are bidirectional, so 100 is sufficient in practice. 1 per station. And 1 network interface card per station. We count as 1 link in that case. Yes. It's a wireless access point, but importantly for this class, it's a switch as well. The 4 ports, if you look at the hardware inside, is a switch. Don't break it because it still works. I think this other one doesn't work. we'll see. We'll see some details of a switch and explain some differences of the types of switches or these central devices tomorrow. Today we need to finish a couple more small things. That's about topologies. One last topology. Hybrid topology combines those together in some way. I could have two segments which use a star topology, or maybe three segments using a star topology, and have three different central devices and connect those three central switches using a mesh topology. So we can combine the topologies to create hybrid topologies. We have a mesh, bus, ring, star, and combine any of those four in different ways to get hybrid topologies. So when we design a LAN, we need to choose the topology. Then we need to choose what transmission medium to use for the links. What technology for the links. And there's no one best answer for what transmission medium to use. It depends on different factors. It depends on what level of reliability we want. How many bits per second do we want to be able to transfer? What level of performance? What's the layout of the building? Maybe we have an old building and we cannot put cables through the walls. What transmission medium should we use? Wireless. If we cannot put cables into the building, then wireless makes sense as a transmission medium. If we have a wired transmission medium, some common cases, at least in the past, coaxial cable commonly used in a bus topology. The old LANs where we have one cable passing by all stations would often use coaxial cable. Optical fibre is commonly used in a ring topology, but not so much in LANs, more in metropolitan area networks, larger networks nowadays. Twisted pair, copper wires combined together in pairs is commonly used for star topology. So this is just one of these cables cut, which has 4 pairs of copper wires together. Each pair is twisted around each other. So this is the common transmission medium used in star topology networks. And there are other combinations possible. Twisted pair is generally the cheapest amongst the different options and easiest to install. We can bend the cables very easily and we can cut them. I can go into the ceiling, cut a cable and join together again very easily. So very easy to install. So, 2 design criteria we've looked at. What topology to use, we've gone through some different cases. And what medium to use, well, there's no one single solution. The last one, which we're going to focus on, is what is medium access control and what approach can we use for medium access control. We saw with our bus topology, if 2 stations transmit at the same time, those signals will interfere with each other and no station will receive data. That's a problem. So what we need is to make sure that only one station transmits at a time. And that's what medium access control does. We have 10 minutes remaining and we need some volunteers to complete this. So follow this because your volunteers need to be involved. If 2 stations transmit at the same time, transmit frames, we say that those frames collide with each other and that those frames cannot be received correctly. We want to avoid such collisions. Medium access control controls which stations can access the medium at what time. The goal, allow only one station to transmit at a time. Therefore, you'll have no collisions. So there are different techniques for providing this, different sets of protocols or rules to make sure that the stations, when they want to transmit their data, only one of them is transmitting at a time. In this class, when we have wireless, it should be only me transmitting and no one else transmitting at the same time. If two people transmit, we have a collision and the receiver cannot understand the data correctly. So when we have computers, we need to program them with a set of rules such that only one will transmit at a time. We can have centralized or distributed control over telling the stations when to transmit. Either we have a special node that tells the stations when to transmit, or the nodes work it out between themselves in a distributed manner. And we can have fixed or dynamic allocation of transmission. So fixed means I've got data to send. Maybe there's a schedule. I can transmit every 5 milliseconds. I can transmit, and then 5 milliseconds later I can transmit again, and then again, and so on. And another station can transmit every 5 milliseconds, but 1 millisecond after me. So one station can transmit, and then I transmit, and then the other station, then I. So we could have a schedule, and that schedule is fixed over some period of time to allocate who can transmit. Or it can be dynamic, in that depending upon what the stations want to transmit, the opportunities they get to transmit may vary over time. So medium access control techniques are about giving stations opportunities to transmit their data. One station has a megabyte of data to transfer, and it needs to send it in frames containing no more than 1,000 bytes each. And another station has 100 kilobytes of data to transmit. Somehow, a medium access control technique needs to give these stations opportunities to transmit their frames. So they have many frames to send. We need to allocate each of them a chance to send such that only one is sending at one time. We're a bit behind our IT section. Why? Not sure. We'll finish there, and tomorrow we'll go through examples of these three medium access control techniques, because we need a good 10 minutes to complete them. And then we'll move on to specifics of standards for local area networks.